Good morning, everybody. Today I'm going to talk to you about some of my research work about shrink-fit weld assembly, and the aim is to consider the shrink-fit part. I'm a third-year PhD student, and I work in collaboration with the Arts Métiers of Metz and the Framatome located in Saint-Marcel. My supervisors are Tudor Balan, Éric Becker, Florent Cusenza, and Thibaut Demol. In the nuclear reactor, the nuclear reaction is located inside the vessel core and is driven by the control drive mechanism, where the passage from the outside to the inside of the vessel is located at the CRGM nozzle. So these nozzles are reparted such as the top picture show it, and every assembly is made by a shrink-fit procedure and is completed by a weld. The shrink-fit part is the fact that the pipe is the dimension slightly bigger than the bore, and the difference of dimension is the interference, and is just a few dozen of micrometer. It's the order of magnitude of the tightness of air, and this assemble is currently justified only with the weld consideration. So this weld should be big enough and good enough to resist and this means that the welding procedure is the longest step for the vessel head manufacturer due to the quality required and the geometric environment. But the welding creates residual stress, which are the main cause for the primary water stress corrosion and cracking, and is responsible for the need of change of several units in the times. And on the other hand, the shrink-fit part is overlooked. So the question we will ask is, what if we remove the welding and we consider only the shrink-fit part? So the shrink-fit strength is made with friction by friction, and the extract effort can be approximate with the Coulomb's model, considering the friction coefficient and the contact pressure. The friction coefficient should be analyzed with experimental procedure. So in this presentation, we will focus on the contact pressure. And the objective of the presentation is to study the shrink-fit behavior while minimizing the weld effect, and to assess the global behavior of the contact pressure over the operating domain. We will consider the temperature between 20 and 350 degrees Celsius, and the internal pressure between 0 and 16 MPa. So to do that, we will follow two mainly approach. The first one is the analytical procedure, and the second one is numerical procedure using Codaster. But in the finite element method is used to study a specific configuration, and in our case, we want to study the contact pressure over the operating domain. So we will extend it with a surrogate model, and we will see how to build it in the following. So in this presentation, we will do a first approximation. We will only consider the central pipe and neglect the other pipe, because with this simplification, the geometry is easier, which enables the use of analytical model, and it will make the computation faster with a 2D model. I propose you the following overview. First, we will see the different method, the analytical and the building of the surrogate model, and then we'll see the different results to finish with the conclusion and prospects. First, let's consider the analytical model. In the literature, the contact pressure for a shrink-fit assembly is analyzed with the fixed cylinders models of Lamé. We consider axially finite cylinders. We submit them to differential of pressure, and then we add two boundary conditions, which is the equality of the radius at the interface and the equality of the contact pressure. This way we can compute the contact pressure, but in our case we want to apply internal pressure, and in particular the one in the internal skill. But how can we do that with infinite axially cylinders? So to do that, we will use a little trick. We will add a first step and consider a thick sphere submitted to internal pressure. We will compute the circumferential stress, which I will present there. Note that it's a tractive pressure. We will relieve the mean value and apply it at the boundary model. Like I said, it's a tractive pressure. We can also take into account the temperature by adapting the contactless geometry with the dilatation coefficient, and the material properties are also dependent of the temperature. So with this model, we can compute the contact pressure analytically. On the other hand, we will do some numerical procedure, but how to consider the weld. In the literature with the course study, we can see that the coaching part and the weld part create residual stress. It's a fact. And in the literature, we saw that we can simulate this residual stress by following the difference procedure. And if we want to do it with Codaster, we can follow the user guide. But in our case, we want to minimize the weld effect. So we want to lock axial rigid motion of the pipe with the least weld influence. And we want to get approximately the same area of contact. So we propose the following situation. We will link the nodes at the bottom of the interface only axially. We will talk about it later. The finite element model that we will use is presented here. Here is the geometry and the associated mesh. The boundary conditions are the following. The internal pressure is applied at the inner skin in green, and we actually lock this part of the vessel head. But to represent the weld effect and to block the rigid motion actually of the shaft, we will only link these two nodes just actually. So now we want to create the surrogate model. We have the feature domain, and we will want to have the quantity of interest. The feature domain, we will consider three features: the interference, the temperature, and the internal pressure. And the quantity of interest will be the mean contact pressure. So if we do that in Codaster, I enter some points, I put it in Codaster, and then I compute the mean contact pressure. But the surrogate model will be considered as an F interpolation, which gives answer close to the one with Codaster. So we'll now see how can we create this F interpolation. We propose a polynomial surrogate model with Chebyshev polynomials, who are recursively constructive by the following reaction. Then we tensorize the different polynomials to get it depend of the three parameter. Each parameter is normalized. We have a basis of 20 polynomials. And then our surrogate model will be a linear combination of this polynomial from the different bases. And the first parameter will be the interference, the second the temperature, and the third the internal pressure. So the question is now, how do we choose the weight? So as I said before, I wanted the answer of my F interpolation close to the one obtained with Codaster. So I will have some points that I will take in Codaster. I will have the answer dependent of W, and then I will have to create an error and choose the W weight, which is the more close, which gives the least error. So let's do that. First, I have to sample my feature domain. I propose to use the small x parse grid with the interpolation of Clenchoker cheese points. Here I have 61 samples, but only 9 geometries. Every point corresponds to an interference, a temperature, and an internal pressure. So first, I have to create the different geometries. So I do that with the API Python with the shaper module. Here is some part of the code. Then I create the different mesh, and then I save them on my computer. Once it's made, I verify the different geometry, and I superimpose the different geometry. At the large scale, I have this picture. When I do a first zoom, I have this one. It's a superimposition. And then when I do another zoom, I have this different penetration corresponding to the different. And we can see that the representation of the interference correspond to the Curtis-Clenshaw distribution. So now I have my 9 geometries. I will have to compute for every point the contact pressure. So I'll go to the Aster Study module. I'll list my different points that I have to see. And then I import my meshing. And here is my code. Here is I parcours the entire list, and for every point, here is my mesh to see, which is here. Here is my temperature to apply, here, and here, the internal pressure to apply. I just want to do a quick note that my simulation will be made frictionless because I want to see the contact pressure on the operating domain with the least interference from the numerical path. If I used friction simulation, my results will depend of the path used, and I don't want this to happen, so I do frictionless methods. So then I print my results, and then I add another steps, which is to compute the contact pressure. So at this point, I get the result from at the interface, and then I compute the mean contact pressure which is obtained with the Lagrangian component. At these steps, I sampled my feature domain, lambda 1, lambda 2, lambda n, my different points. And for every point, I have the answer obtained with Codaster simulation. I can vectorize this equation, and then I can create an error and find the W vector corresponding that minimize the error. So I define the first error, which is the Euclidean measure, and then I add regularization to limit overfitting. So this is this weight vector that I will use. So now that we built both the analytical model and the surrogate model, we want to see the different results. So first, we have to check if the surrogate model gives good answer. So first, we validate it on the training results. We see that the results are very close. And then we will create untrained data and check if the results are correspond well with the Codaster procedure and the numerical model. So at this point, I create only 5 points inside the interference domain because every point corresponds to a specific geometry. And then for every geometry, I generate 30 random points, and I do the same procedure as explained before. And I compute the error on the domain. I see that the contact pressure error is very limited, and the main error occurs for the low interference. Then I watch the the results on my whole operating domain. So how to read this graph? The first column is analytical model, second one is the surrogate model. For every line, we have a specific geometry. And for every graph, every point corresponds to a specific temperature, a specific internal pressure, and the color gives us the contact pressure. So we can see at the first order that if we improve the interference, we improve the contact pressure. If we improve the temperature, we improve the contact pressure. But if we improve the internal pressure, we reduce the contact pressure. It is due to the fact that when I put an internal pressure, I add a tractive pressure at the extreme. So now we can see the difference between these two models. We see that we have the largest error for the low interference. It is due to the fact that for the low interference, we have such a large area that we lost contact and it's difficult to predict then. But for higher interference value, we see that the error is contained and doesn't depend much of that of the interference. I told you before that I did only frictionless simulation, but what if I took a physical path and I simulate it with friction? What is the impact of the friction? So I consider this path, and then I show you the different results obtained analytically with the surrogate model and friction and frictionless results. We can see that first that the surrogate model is very close to the model with frictionless. It's because it trains from it. So, and we see that friction and frictionless results are also very close. We see some difference, but this means that on this specific path, the results depends more than the thermomechanical condition than the path we use. To conclude this presentation, we see that internal pressure push further the bore than the outer surface of the patch, which creates loss of decrease in the contact pressure. We see good consistency between analytical and surrogate model. And we see that on the studied case, friction has few influence on the mean contact pressure. This will need a further study to confirm it on the operation domain. But results are only valid for the central pipe and this simplified weld, which is considered where we minimize the weld. But the methodology can't be adapted for the analytical model on peripheral pipe due to the complex geometry, but it can be adapted for the surrogate model for the peripheral pipe. I just want to finish with two prospects. The first one is the peripheral pipe. If I study a peripheral pipe and I look at the interface, I have a cylinder. I want to study it with cylinders coordinates, but during the transformation, my pipe moves, so do the axes. So I have to compute another axis during transformation to have precise results. And the second prospect is the push-out test. I will do shrink fit procedure on the particular assembled, and then I will want to study it numerically. I have two means to do that. First, with first control procedure, which is made in this study with ANSYS and Abacus. I make my assembly and then I push till I have a divergence in the results. The question is, if I do that and I have a divergence, is it because I lost contact or is it because of other problem? To see, I can do overly. I can do a displacement control procedure which is made in the study. But in this case, I want to have a criterion problem. At which point can I consider that I lost the contact? So thank you for your presentation.